So maybe we can start now this workshop. So my name is Frédéric Giraud, and I say to all of you, good morning, good afternoon, or good evening, depending on where you are on Earth. So welcome to this workshop on the multimodal augmentation of haptic touch input. So I think that you can hear me easily. First of all, this workshop is carried out within this IEEE World Haptic Conference 2021. And I would like to thank the organizers of this conference to let us organize this workshop and to provide us with the necessary technical assistance. And for that purpose, I would like to thank Madi, Tavakoli, David, Abink, and Itzan Tirzaf, who is our student volunteer, to help us with the technical issues that we may have during this workshop, and who help us to prepare this workshop as well. So thank you to all of you. Before going to the first presentation, I would like to briefly introduce the workshop and its the workshop and the motivations for this workshop with one slide. I won't be too long. So okay. So we start from the fact that today we are using more and more tactile devices, touch input devices on tablets, smartphones, but also in virtual reality. And the fact is that paradoxically, the devices are more accessible to people because they are very cost effective. But a segment of the population now is excluded from these digital developments. Because they have visual impairment, because these devices indeed rely a lot on visual feedback, or because they have motor impairment and they cannot easily touch and have gesture on the devices. Therefore, there is today a strong need to provide or to develop applications and devices that can work for everyone. Maybe for that purpose, introduce more haptic feedback into these touch input devices can help to solve this issue. So we want to use more multimodal devices, multisensory tactile devices, but there is a theoretical question here is how haptic integrates with the other senses. And this is the core of our European project, which is called Multitouch. And speakers from this workshop today, some of the speakers are indeed involved in this European project. And you can follow the results and advances of this project with this address web link here, which is given here. So this workshop has 6 presentations, and we will have a break after 3 presentations, and you will ask questions after each presentation as well. So the first presentation is given by Olivier Collignon from Université Catholique de Louvain about how vision shapes how we feel touch in space. And Olivier, if you're ready, I stopped my screen sharing. Yes, and the floor is yours.
Yeah. So you should see my slides.
Yes.
Yeah. Do you see them? This.
Yes, it's clear.
Okay, perfect. So yeah, thank you very much for the organizers, obviously, for organizing this this very nice workshop. As it has been said, like the main framework is organized under this ITN network, where we study and develop some tools related to the sense of touch. And my goal in this project, somehow in my lab, is to focus on this part of the population for who sometimes these devices are developed, like, for example, blind people. But what I will try to stress here, or at least provide example, is that somehow they process touch, and particularly touch in space, in a particular way. And we probably need to understand that or know that while developing these devices. So obviously my talk is not on the device part, but mostly on the cognitive neuroscience of the sense of touch. Like I've said, what we will study here actually is the perception of space by blind participants, and in particular, how they process touch in space. And the question, therefore, is how does the experience of vision influence how we perceive touch in space? And why actually is this an interesting problem? Yeah, we probably all know that vision is a very dominant sense when it comes to spatial perception. Probably a very easy and trivial way to illustrate that is to speak about what we call the ventriloquist effect, right? So we have all experienced, or have seen these shown of this ventriloquist person that obviously speaks basically with the stomach, is the definition of ventriloquism. And because he moved the mouth of the puppet at the same time, you believe sincerely that the sounds comes out of the mouse puppet. And it's a very clear example of how you recalibrate actually the perception of the auditory spatial information toward vision. You can actually study the phenomenon very easily in the laboratory with a simple setup of flash and lights, like illustrated on the left side of this panel. And for example, what you can do is present an event, like for example, here just in front of the participants, and right after, without telling, and this event will be an audiovisual event, so a flash and a beep at the same time. And just after this event, you will present another event, and without telling the participants, you will separate the position of the flash and the beeps, right? So for example, the beeps will be on the left and the flash will be on the right of this first audiovisual event. And you ask the participant whether the second event is more on the left or on the right. And what you will see is illustrated in the graph on the right side of the panel is the number of time the people respond toward the direction of the flash, right? And especially when things are presented right in front of the participants, where the vision is the best, the foveal vision we call it, people typically almost 80 or 90% of the time choose the direction of the flash, right? So they really have this very strong visual capture of the position of events. So people truly believe that the audition also came from the side where the flash was coming from. It's actually this visual dominance is well known also in the brain, right? For example, these are very elegant studies that have been done in the recording neurons of the optic tectum of the barn owl. Here is an animal that chase using audiovisual information to locate its prey, like for example, mouse, for example. And this barn owl in the optic tectum has actually neurons that are multisensory. They respond to vision and to audition. What you can do actually is raise the barn owl with prismatic deviation, right? So each visual event will be deviated of some degrees, for example, toward the right or toward the left. Obviously, therefore, this creates a mismatch between the position of sounds and the position of vision in external space. And if you do that in the developing owl, what the researchers have demonstrated is that the neurons, so the receptive field of the neurons that are sensitive to the position of the auditory information in space, recalibrate toward the position, the receptive field of now the deviated position of the visual information. I know it might have been a little bit dense as in information, but just in a nutshell, what I'm trying to illustrate here is that vision is so dominant in your perception is that if you deviate with prism the position of the receptive field of visual information, it will induce an immediate recalibration of the auditory receptive fields to merge with those of vision, right? So again, illustrating visual dominance when it comes to process multisensory space. And I've given examples in audition. Obviously, the goal of today is more to study the sense of touch. And there is this one illusion, probably most of you have heard about it, the rubber hand illusion here. It's a very small video illustrating it here. I will explain a little bit later what is happening here. But what you have seen here is actually that the participants really truly believed that his own hand was attacked, right, by this fork, right? And how is it happening? It is happening simply because if you take this rubber hand and you ask the participants to look at it, and at the same time you brush this hand, you brush the real hand of the participants that is not seeing because of this panel. Even if the participants obviously know very well this hand is not his own hand, right? Because trivially here, what we can see is that it's a mannequin hand, right? But because he experienced seeing these fake hands and feeling something on his hand at the same time while this fake hand is brushed, he cannot avoid to believe this is his hand, right? And therefore, if something is attacking this hand, he will remove his own hand, right? He truly embody the position of this hand, right? Simply because he's seeing it being brushed. And again, this is a very clear example of how vision somehow creates some kind of recalibration of a multisensory event, like for example, this time tactile event. And this is happening actually constantly in our daily life, even in situations that we don't really realize are necessarily ever linked toward the visual system. If a mosquito starts to hit your skin and starts to beat you, obviously the first reaction will be to look at the position of the mosquito on your hand and try to smash it with the other hand, right? So here, if it's positioned on your left hand, what you will do is that you will look at this mosquito on your left hand and probably do a motor command action of your right hand to go and smash it. But this is actually a problem in daily life that is far from trivial. We do it seamlessly, but it's actually a complex problem. And part of the complexity of this problem is because our limb moves in space, right? So this left hand, right, might be up, right, close to my head, can be down, can be in my left side of my body because this is my left hand, but my left hand can move in space, and actually my left hand can also be positioned on the right side of my body, right? So basically the position on the skin does not tell us nothing about the position in space, right? What you need to do is to recalibrate the position of the tactile stimulation of your skin in external space, because if you don't do that, you don't know where to look at and how to act with the other hand to go and smash this mosquito, right? And this phenomenon is well known as external remapping of touch, right? So instead of just localizing touch on your body, which will not be useful because again, your body moves, and therefore to create an action, you need to know where your body and the sensation on your body is located in external space to do an action on this position in external space, for example, with the other hand, right? And a very simple, again, psychophysics illustration of this problem can be done with what we call the temporal order judgment task. So again, it's a psychophysics laboratory task where we ask the participants here, which of his two hands has been touched first. So I will touch, for example, with a tactile stimulator, the left hand and then the right hand, and the participants have to tell me the left hand was touched first, and we do the reverse. And for example, we do this electric stimulation, for example, or it can be anything. And then the participants has to report to me which hands has been touched first. And what we will do is that we will play with the interval between the two tactile stimulation, and we will make it shorter and shorter up to the moment the interval is so short, right, that you cannot really know which hand has been touched first, right? So, but you can draw a very nice psychometric curve. I will show you some example of that, of like how much, what is your performance in such a task. But the trick you can use in this task is that you can also do the exact same task with a crossed posture. So why is it interesting? It is interesting here because now your left hand, right, the left side of your body is positioned in the right side of external space. So we create on purpose a mismatch between the somatosensory, the egocentric coordinate, and the external coordinate, right, which we believe might be linked to vision, and I will illustrate that a little bit later, right? So this is the simple trick, very simple setup. And what we do, like I said, we present stimulation either to the left hand first or to the right hand first. So what you just have to do is to compute the delta of the temporal delay between the arrival of the signal in your brain between these two stimulations and make a judgment. And how we illustrate that, right, as I said, is using a psychometric curve where basically in the left side is the when the stimulation is presented first on the left hand, for example, okay, and on the right side of this curve is when it's presented more on the right side on the right hand, sorry. And the delay, the difference of the delay is the distance in time between the two stimulations. So the closer you are from the middle point, the shorter the distance on your left hand touch first. Just after this point of subjective simultaneity, is your right hand has been touched first, but with a very small temporal gap. And if we go here on the x-axis, it's your right hand has been touched first, but you know, a lot of milliseconds before the left hand. I hope it's clear. And here, what you plot here is the proportion of right hand response, right? So obviously, if your left hand is touched first, you give a little amount of response right hand. When your right hand has been touched first, the amount of right hand response dramatically increase, right? So, and you have these zones here in the middle where, you know, you do mistakes, you have uncertainties. And if you do this task in the lab, so let's focus first on this curve with the open white dot here, right? It's the uncrossed posture, right? And in this uncrossed posture, we have basically the same psychometric curve I just explained, right? So if your left hand is being touched first, like for example, 300 milliseconds before the right hand, you rarely say basically your right hand, right? Because it's your left hand. Then if you go closer in time, like 50 milliseconds before the right hand, you start to have a little bit of response right hand. Then you move to the other side. So your right hand is touched first. Up to 300 milliseconds, you do some mistakes, right? And then if it's touched 300 milliseconds, the right hand first, you always say right hand, right? So it's this nice psychometric curve. Okay, and this is true for any condition. I will not enter too much into the detail. This is as illustrated here. Now the interesting bit is this black curve on the top of it. The black curve is actually extracted from the crossed posture. And you clearly or immediately see that something different is happening. If you think about this task, you should not care that your hands are crossed or not. It's a pure timing task. Which hand has been touched first, right? So if you have two primary somatosensory cortices on the left, on the right, you should not actually be really impacted. But what we see is that the performance is massively impacted. And what is happening actually is when your left hand is touched first, but if your left hand is not in right space because your hand is crossed, you start to give a lot of right hand response. You basically have the illusion that your right hand has been touched because actually your left hand is in the right side of space. And this is true for the right hand, right? Now you see that you have a lot of response, little response right hand, so a lot of response left hand, even though it's your right hand that has been touched here, simply because this right hand is again in left space, right? So again, to summarize what I've trying to convey here from these graphs, the fact that your right hand is in left space creates a mismatch between these two coordinate systems, the somatosensory coordinate system and the external coordinate system, right? And this mismatch creates sometimes this illusion that actually the wrong hand has been touched because actually your hand is in the wrong side of space, if you want. It crossed your body midline. And so after observing these effects, researchers were wondering what drives actually these effects. And an idea was that actually it is our visual experience. To go back to the introduction I just did, that maybe our visual experience drive the way actually we experience these things. And actually, this is what this study illustrates here. So we see here the performance. It's a complex graph that I took from this paper, but okay, maybe we can, again, here it's the same graph. So it's like on the left side is left hand touch first, right side is right hand touch first, right? And you have the performance when the hands are parallel or the hands are crossed. We don't see it well, but if we look at the sighted here, we don't see it very well, but the performance, so the steeper, the better the performance of the uncrossed hand is here, and the crossed hand is here, right? So you see a very strong decrement of performance. If you look at the congenitally blind people, right, you see actually that the uncrossed and crossed posture superimpose each other. So basically they are not impacted by this manipulation of crossing the hands. It's actually illustrated here is what we call the just noticeable difference between the tactile stimulation of the two hands, where you see in sighted people that actually you need much longer interval between the two hands to have good performance compared to in a crossed here versus uncrossed posture. And when you see in red here, the congenitally blind subject, there is absolutely no difference, right? First, they are better, the blind, and there is no difference between the cross posture. And the late blind, people that acquire vision, have the same performance or the same impairment in performance in the crossed hand effect than the congenitally blind participants. So it seems that really the absence of experience of vision prevent touch to be remapped in external space and therefore to experience this conflict. We reproduced in the lab this experiment, and here in a nutshell, basically we were able to perfectly reproduce these results. So these are very reliable results where you see that in sighted participants, sighted controls, you have a dramatic difference between the uncrossed and the crossed posture. But in early blind, you have absolutely no difference between the positions, right? Between to have good performance in telling which hand is touched first. And what we were interested is to see now what are the neural correlates of these things. So basically, again, here, what we did is the same task, right? But while we were recording the activity of the brain of the participants while they were lying in an fMRI, so a magnetic resonance imaging scanner, and we were recording their activity. So what you see in the sighted participants is the performance in the uncrossed posture in black and in cross posture in red. So you see this massive reduction of the performance when the hands are crossed. In the blind participants, we replicate for a third time the results. No difference between cross and uncrossed posture. What's happening in the brain? So what's happening in the brain, if you contrast in sighted people, which brain regions activate more when the hands are crossed versus uncrossed, you have a network of regions, including the right dorsal stream, right? These regions actually are very important and are believed to be the neural substrate of this external remapping of tactile information. So this is in sighted participants when we contrast crossed versus uncrossed stimulation. Again, from a physical point of view, this is the exact same stimulation that have been delivered, right, to the participants. If you do that in blind participants, like their behavioral performance, you don't see any difference in their brains. Like if basically they do not activate these networks of external remapping in the crossed posture, right? Simply because they simply do not experience this phenomenon. And then this is the map when we contrast directly the two groups, the sighted group versus the blind groups, okay? What is more activated in the sighted versus the blind, in the crossed versus uncrossed posture. And again, we find back this network to really show that this network composed of parietal and prefrontal region that is involved in external remapping of touch, in basically resolving this conflict of the frame of reference of position of space, is actually only present in sighted subject and not in blind participants. I will skip this last one. And what is interesting, because we were wondering at that time, at that moment, it's very strange because what we observe here is that if the blind were not relocating touch in external space, but that should be extremely problematic for them, notably when they navigate and when, for example, they use the wide cane to navigate. So we were really wondering if it's actually this external remapping of touch is present in every situation. And so the trick we used here in this part of the experiment is that we separated what we call internal versus external instructions. So here we do exactly the same thing, right? We touch one hand after the other. It's a TOG task. And just I highlight here for the purpose of the explanation here that which hand has been touched first, right? And here, for example, we touch first the left hand, right? And what we ask the participants in the internal instruction is to react with his left foot, right? Not with his hand, this time with his left foot, but something that is coherent from a somatosensory point of view, from an internal somatotopic point of view, right? So your left hand is touched, you respond with your left foot, whatever the position of your left hand, right? If your left hand is in right space, you still press with your left foot. So internal instructions. External instructions, actually, we force the participants to process external space. If your left hand is being touched first, and if your left hand is in left space, you push with your left feet, like before. But now, if your left hand is in right space, we ask you actually to press the button with your right feet, right? Because now your left hand is in right space. So what the side of space that has been touched first is the right side of space. So now let's look at the results. So in this condition, actually, it's very similar to the previous conditions I've presented to you. We again replicate the exact same results. What we see is that in the sighted subject, we don't see the curve of the sighted in the parallel position, but it's here. It's very different from the position when the hands are crossed, right? So we see this reduction of performance again in the sighted. In blind subjects, the red curves, full line or dashed line, what we see is that they superimpose these lines, right? So it's a replication. So under internal instructions, again, the blind people, they do not remap touch in external space. They do not experience this conflict. But if we now force them to process external space with external instructions, what we see is that now the level of impairment of the performance is even stronger in the sighted, but now we see it appearing in the blind, right? We see that there is now a difference with the full line and the dashed line, red line in the blind. So basically they start to do mistakes compared to the uncrossed positions, right? So what does these results tell us actually? It tells us that it's not that the blind do not process touch in external space, but probably the blind are more flexible in the way they do that, right? So they actually, if you ask them to resolve the task with internal instructions, they do not experience the problem, actually, because you do not need to remap touch in external space. But if you do, by forcing them to process external space, then you will start seeing this conflict appearing in your data, showing that actually also the blind experience this conflict between somatosensory and external references. I'm not keeping track of time. I don't know if I still have time. I think I do. Can you
maybe 3-5 minutes?
Okay, that's perfect. So I will illustrate a last experiment where we actually again show how interesting it is to study these things. And another example where we process some kind of somatomotor information in space is when we learn tactile sequences. So I illustrate that again. I started with a film reference that I like from Kubrick. Now it's another film that I like very much, Amadeus from Milos Forman. And here in these experiments, they take Mozart here, and he's playing a piano in a typical position, right? But what they will ask him to do, right, to entertain the people in this party of that time, is to play piano backwards and with his hand crossed, right? And actually Mozart was known, apparently reputed to actually, he could play basically piano in any position, with his body in any positions actually. And what does that tell us? It tells us that when you learn motor sequence on an external device, like for example a piano, you not only create a representation of the sequence on your body, which fingers I have to move, but obviously to act on this external object in such a position, you need to create a view from above, right? You need to create what we call an allocentric representation of the position of these keys in external space. Otherwise, you will not be able to play the piano if you were to reproduce the same motor sequence in such a position. Obviously, you will not play the same song. right? So you need to basically have two types of representation: an egocentric representation linked to how your body should move, but also an allocentric representation of how things are positioned in external space, somehow independently of the position of your body. And again, in the lab, we can use that with a very simple trick. We can make people learn a motor sequence on a keyboard like this, right? And then test them with the keyboard presented upside down, right? You just switch the keyboard upside down. And we ask the participants to either reproduce the same motor sequence, what we call the egocentric conditions. They just have to reproduce the sequence of their fingers. If it's like middle finger, then pinky, then thumb, they have to reproduce that, even if the keyboard is upside down, or the allocentric reference, right? Here, it's not the motor sequence that you have to reproduce of the fingers, it's the position of the keys in external space, right? So if, for example, the first key is 4, now the first key upside down is 1, right? Because the position of 4 now, as the position of this key here is now here in external space. So it's because we flip, right, the keyboards. And so we know, we do that 2 times with each participant, because we do one with two separate sequences to test the ego and allocentric conditions separately. And very quickly, what we do is that we do a training phase. Obviously, what we see is that they improve, so they do less mistakes and they go faster to do the sequence. This is in black the performance of the sighted participants, in blue the performance of the blind participants. And what we compare is that, and here the transfer period is when we flip the keyboard upside down. And what we compare is that the effect of flipping compared to the starting position when you have to learn a new sequence. And if there is a difference between these two things, if this goes faster or better than this, it means that you have learned, right, the sequence, either the motor sequence or the allocentric sequence. And what we can see here is that in an egocentric perspective, when we ask the participants to do the same motor comments, we see that the performance is better. They have learned the sequence. Now, what is interesting is that in the allocentric conditions, where they do not have to reproduce the motor sequence, but the position of the keys in external space, right? What we see is that people also learn the sequence, actually. So people build this external model of the position of the keys in external space, otherwise they will not be faster in this transfer period compared to the start of the sequence. And this is also true in early blind participants. And this was a little bit surprising to us, right? Because if we go back from the first TOG experiment, we have seen that the blind people do not automatically remap things in external space, right? So what we believe here is that actually as soon as the blind act in the world, so act on a device, like for example on a keyboard, they actually represent, they create this external representation. It's only if you put them in a condition where they do not need to do that, like in the TOG task with internal instruction, that actually they do not. Us sighted, we cannot avoid it. We have to do it. So in conclusion, what I've said is that vision drives the automatic remapping of touch in external space. Coincident blind people actually can activate external space if the task requires it. And what we believe is that any time there is a motor command, an action on space, then the blind people will activate this external representation. So why do we think these studies are interesting is because, again, it tells us that maybe blind people in some specific conditions process tactile information or motor action in a different way, and that probably can help us to design actually better tools and sensory substitution device and so on in the future. So we will continue to work on such topic in the project Multitouch with a PhD student. Her name is Ikra, actually, that's been hired in the project Multitouch, and she will bring these studies to the next level. And I will finish by thanking my collaborators and my lab funding agencies, and obviously thanking you for your attention.
So thank you, Olivier, for your clear and very nice presentation. So we have time for a couple of questions. So to ask questions, so the participants, you can raise your hand. In the you can raise your hand. You have something in the menu, Zoom menu for that. And then you can ask your question directly in the chat window, and I will reproduce your question. not be shy. So maybe I can ask a question to you, Olivier, about do you have any ideas on how to use these findings to create devices that can that can work as a substitution for blind people, or to
Yeah, I mean, this is again, it's a very good question. Obviously, we are still trying to think about how this will influence the design part, right? But I think also, I mean, this is true for the blind, but this is also true for the sighted. Again, like for example, a huge application of the haptic field is, for example, equipping cars, right, with these screens. And you will not have to look at these screens. You will tactily interact with them while you are driving and continue to watch the road, right? But again, the way you will interact with these screens is not necessarily determined, right? At the moment, like Tesla decided the screen is like vertical like this, your hand is positioned like this. But again, this creates an interesting questions about like how your hand is, the position of your hands is the best suited, right, to interact with this device, to create really an interaction, a position in external space that will prompt you toward the right directions, right? If you want to have a tactile feedback that tells you, oh, be careful, you have to move to the right side, right? Because something is happening, you have to be sure that given the position of your hand, right, you stimulate the right part of the body, right? It's not necessarily that you need to stimulate the left side, the right side of the hand to induce a right movement. If your hand is positioned, for example, upside down, right, you will need to produce the right direction to stimulate not the opposite side, if you want, because this will be in external space. And for example, so this is an example of how like these things may actually influence the design of things related to the blind. Again, like I think if they do not automatically remap touch in external space, this may actually also potentially influence the way you will want to give them tactile feedback, or at least the way also you will want to instruct them of how to interact with things, right? And have this maybe active component and not passive component. So you mentioned sensory substitution devices. Some sensory substitution devices are extremely passive, right? So you take the visual information and it reproduces something on your body, right? But you do not move, you do not interact with these things, right? And that might actually be a key component. This motor action, right? When you look at something, you don't realize, but you move your eyes, right? So you really explore, you scan the environment, you actually do a motor action on these things. If this is replaced by a camera that takes pictures and reproduce with a tactile sensation of your body without that there is any type of exploration of these things, that might actually be very problematic, actually. And then this component of like having sensory substitution device that create this sensory motor loop, basically that your body interact with the environment and not that the environment imprints on your body, you know, like implicitly, might actually be something interesting or important.
Okay, thank you, Olivier, for these comments as well. It was very interesting. So I do not see any other question in the chat, and nobody raised their hand. So we can maybe thank you again and move to the next presentation, which is given by Monica Gori. And so Monica, you can share your screen maybe. So
yes.
Monica from Italian Institute of Technology.
Okay.
So we have, okay, so we can see your screen and it's full screen. So the floor is yours. Thank you.
Great. Can you see it? Okay.
Yes.
Thank you. Yeah. Okay. Thank you very much for the invitation. I think we decided to do this workshop because of of the multi-touch project, and it was a very nice occasion to have an interdisciplinary group of researchers working together in a very interesting topic. Today I will present you in the first part of the talk our results on technological solutions for children and adults with visual impairment. And in the second part of the talk, one of the PhD students involved in the multi-touch project will present the first experiment done within the project. So I'm leading the unit for visual impaired people. We are in Genoa in this building here, and we are in IIT. The group is composed by half psychologists and half engineers. Our goal is to understand the multisensory development in typical and children with and without visual impairment. And the second goal is the development of new technology for early intervention. This is the approach we use. So we study from the understanding of the brain, I mean, with the behavioral and EEG mainly works, and based also on the works that, for example, Olivier just showed to us. So the basic science is the starting point for the development of new technological solutions, and then we use it in the society with users, rehabilitators, teachers, and we again validate the technology at the scientific point of view based on behavioral and neuroscientific findings. We use usually a methodology based on motor responses, psychophysical quantifications, modeling principally with the Bayesian approach, and EEG mainly, and recently also some fMRI works. We develop different technological solutions that are mainly wearable solutions, and I will show you now some examples. Our work is focused on people with the visual impairment, and mainly children with visual impairment. In the world, there are about 20 million of children with visual impairment younger than 14 years. There are many solutions developed for blind individuals, but we have recently made these two reviewers papers in which we have analyzed all these technologies, and we have found that just 2 of them were for children. So there are some devices, such as the long cane, that can be used also during the development. So it is very interesting to think about why some technological solutions can be used, and which are the key features in order to develop new technological solutions useful for children. Our idea is that to arrive to children, we have to have some very simple technology that uses the brain as the main, let's say, mediator, because as in the long cane, we have the person doing the movement and the person perceiving the feedback of the long cane, that is tactile feedback, acoustical feedback, is the brain making all the process. And this is maybe why young children can use the long cane. So based on this idea, we have recently developed the ABBY device. ABBY is an audio bracelet. I will show it later in the next few slides. So I will try to present you this approach for the ABBY project, and then in the Maria presentation, we are just at the beginning of the multi-touch project. So the scientific feedback we can give to the development and the improvement of the technology within the multi-touch project. So for what concerns ABBY, ABBY has been financed by European Union, and I was the coordinator together with Gabriel Bodbovi. The idea associated with ABBY is very simple. I mean, this is my young kid when he was 5 months old. As you can see, if I put a sound here, it can has an auditory feedback to body movement. So let's make an example. If I'm sighted, when I move my hand, I can observe my hand. But if I'm blind, I cannot. However, if I put the sound on my arm, I can listen my body movement through the audio position in space. And this is an example of the use of ABBY in a social context. So I'm interacting with a sighted blindfolded person. As you can see, by listening the sound of the device, she can follow the sound and she can reach the object. So Haptic is very simple and very intuitive because it doesn't need to learn a new language. It doesn't need to understand some complex, new features, and it doesn't require so much attentional load because you just need to listen a sound and to localize it in space associated to your body movement. So we have used Haptic in different settings with blind and sighted individuals in short trainings of 1 or 2 minutes. And then we use the device in a longitudinal training of 3 months. In this training, we involved for 69 hours and 12 weeks, 42 children. Half of them were trained for 1 hour per day and 1 hour per week at the rehabilitation center with Haptic, and the other without Haptic. These were children from 7 to 17 years of age. Haptic was associated to an application that allowed to change the frequency, to choose the kind of sound we want to produce, and it contained an accelerometer, so that when I stopped my movement, I didn't perceive any sound. Haptic was developed thanks to an association with user-centered designers, and that involved a group of children, of blind children, in order to understand the best sound to be used and the specific games to be developed. And then we developed games with this device in the rehabilitation center. These are some examples. This is a blind child running, and yeah, it's quite unusual to see blind children running. He was running by listening the sound produced by the bracelet of the rehabilitator. As you can see, she can follow the rehabilitator without any problem. In this case, this is a younger child. He was strongly low vision, but we blindfolded him to be sure that he couldn't observe, and he was listening again the sound. Here there was a group of children playing together. They had to find the chair associated with each Haptic. And this was a group of children passing the Haptic device. So as you can see, it was possible to make individual trainings and also social trainings. We observed that the experimental group had very strong improvements after the use of the device in the post-training compared to the pre-training. And it was evident also for those tasks that was just motor. For example, path reproduction, in which they have to go and reproduce the movement with the hand or by walking, or the go and come back test, in which they have to walk for 3 meters, turn, and then come back. The same improvement was not evident in the control group, who did the typical rehabilitation without Haptic, and the improvement was still there after 1 year. So it has been shown that during the first months of life, association between visual information and body movement is very crucial for the development of space representation. This visual motor association seems to be associated to the ability of the child to develop reaching abilities. So when the child starts moving his hand and observing it, they understand that the moving hands are his hands. So he starts using these to reach for objects. In absence of vision, the sensory feedback associated to body movement is not possible, because without vision, the body movement is not associated with any sensory feedback. So our idea is that Haptic is giving back this sensory feedback associated to the body movement, and it allows to recreate a bridge between body movement and the space. And in some way, thanks to this auditory feedback associated to the body movement, children start to better represent space, the audio space, and also their motor behavior in space. So together with these psychophysical results, we also had very good feedbacks from rehabilitators. For example, ABBY allows to refine the capacity to listen to a sound in space. It allows to improve the spatial abilities and child orientation, such as far, close, up, and down. And it can make possible some games or traditional groups activity that are not possible without this device that promotes the relationship among peers. We have recently, these are very new data, the paper is still in preparation, in which we have replicated the same training, similar training in adults. And these are 3 long-term late blind adults. We did together with the behavioral experiments also EEG experiments to see whether the use of the ABBY device also changes the representation of spatial sound at the cortical level. And so these are some of the trainings we did with 3 participants for 1 month, 1 hour per day. So in this case, he has to reach the sound. Here he has to follow the sound. Both were in the peripersonal space. No, it's not working. And then we also trained them in the space. So they have to follow the rehabilitator or to avoid an obstacle with the ABBY device on it. Also in this case, we observed good improvement for sound localization after the training, path reproduction with the hand, and also we observed the cortical localization. What is very interesting is that both in this case and also in the other case with children, we found that ABBY didn't improve anything in depth. So this is a very interesting point that we are now investigating. What we observed, as I said, I don't have a long time now to explain the results, but is that after the training, we observed that there was a cortical reorganization. So the visual cortex of blind individuals after the training represents response to the contralateral position of a sound in space. So, and this is what sighted individuals do. While before the training, they behave like early blind individuals. So they respond not to the audio position in space, but to its position associated with the temporal delay of the stimulus. So we found a very nice reorganization also at the cortical level. So these results suggest that new sensory motor association can restore spatial representation. They can also improve the quality of life of these people. And this is a late blind individual trained with ABBY. So as you have seen, this is, I mean, very natural feedback that can be used in different contexts. We have now optimized the ABI device with, I mean, a kit that can be, distributed in hospitals. And yeah, so I have shown you an example of how, starting from the understanding of, the basic principle associated with the brain development, it is possible to develop technology, to try it in the society, and to validate the device. What I think is also important is that the device can also be used to validate scientific theories, because if we hypothesize that the benefit provided by, for example, the association of audio-motor information can restore audio processing and also cortical activations, then it may suggest that this sensory motor feedback is very important for the development of space representation in absence of vision, and that the vision modality is mediating that process. So in the lab, we are doing different works associated to different aspects of space, mainly space representation, and by following the same principle. And within the multi-touch project, we have now started doing this kind of interaction between psychophysics and technology. So as I said before, we are at the first stage of the processing, and Maria is just started the PhD, so she will present the first experiment. The idea is that tactile feedback can be integrated with audio and visual feedback in the next generation multisensory human-computer interfaces, and it is very important to know how, for example, as also Olivier said before, the tactile system should act in order to integrate optimally information with audition, and also to perceive our space representation in an optimal manner when we are sighted or when we are blind or deaf. So I will leave now the second part of the presentation to Maria.
Thank you. Okay, Mario couldn't make it to this presentation, but he recorded the video for us. I will play her video now.
Hello, everyone. Well, I am going to present the work that we have done so far within the multi-touch project. With it, we try to answer to some scientific questions such as how unisensory and multisensory perception work in audio-tactile integration, and which is the role of active touch in multisensory audio-tactile perception. In order to address that, we designed two experiments. The first one is audio-tactile integration during passive touch, and the second one during active touch. This is the method that we follow. We studied the velocity discrimination threshold in two alternatives for choice. We had two standard speeds, that is 3 and 7 centimeters per second, plus 2 quests. The participant has to perceive a sequence of 2 movements and discriminate which is the faster between the two, the first or the second. We have one stimulus during 1 second, then there is a pause, and another stimulus during another second. Here you have a video. First stimulus, and the second one. We had a tactile condition in which the information is provided by the movement of the wheel that has some sinusoidal greetings, as you can see here in the picture. In our case, it's 10 cycles per centimeter. Then we have an audio condition in which the sound is provided by this device that is attached to the wheel, so we can hear the speaker moving. And finally, a bimodal condition in which tactile and audio information are simultaneously presented. Our hypotheses were that we were going to find a better performance in multimodal compared to unimodal condition, as some authors have found that when the information comes from multiple senses compared to a single one, the performance is typically enhanced. Also, we expected to find some difference between the active and passive movement, as some authors have already suggested. And we speculate about some difference between fast and slower velocities. We extracted the psychometric function for each participant for each condition. The psychometric function is the representation of the proportion of faster responses for each standard velocity. Here you have the 3 and the 7. From that psychometric curve, we extracted the GND, or just a noticeable difference. That is the amount that something must be changed in order to this change to be perceived, and also the bias. Here we have the GND for the first experiment for the 3 centimeters per second standard speed in 15 sighted participants. And we can see a benefit in the perception when both modalities are presented simultaneously compared with the unimodal condition. On the contrary, we cannot see any integration for the faster velocity, that is the 7 centimeters per second standard speed. Here we have the bias, and there is no significant difference between them as we expected. So we can conclude that for passive touch, multisensory integration of audio tactile speed occurs for lower velocities, but not for higher. The method for the second experiment, that was audio tactile integration during active touch, is exactly the same as the previous one, but the participant has to move the finger in the opposite direction of the wheel, as you can see in this video. Here we have the GND for, again, 15 participants for the 3 conditions for the 3 centimeters per second standard velocity, and we cannot find any multisensory integration. But for the 7 centimeters per second standard speed, we see a benefit. Again, no difference between the bias. So we can conclude for the second experiment that during active touch, multisensory integration of audio tactile speed occurs for higher velocities, but not for slower ones. When we compare the passive and the active touch, we can see that for the 3 centimeters per second standard speed, there is a benefit in the bimodal condition for passive touch, but not for active. While for the 7 centimeters per second standard speed, the reverse is true. We can see some benefit for the multisensory integration for the active, but not for the passive. The conclusion is that these results might indicate 2 different processing of multisensory integration for active and passive speed perception. The passive could be more adapt to integrate multisensory signals that are slower, while the active touch could be more adapt to integrate multisensory signals that are faster. The implications that can have for new devices is that if we want to benefit for audio tactile integration during passive touch, the multisensory signal should be slower, while if we want to benefit for audio tactile integration during dynamic touch, the multisensory signal should be faster. And that's all. Thank you very much. I am sorry for not being able to be there in presence. Here you have our emails in case you want to contact us, and that's all. Thank you very much.
Okay, thank you. So we can ask questions for both presentations. So again, if you want to ask, you can raise your hand or write a question in the chat window directly. So no question for the moment. So if you prefer talking, you raise your hand and okay, so we have a question. So Corentin Bernard, you are allowed to talk now. So you can switch on your microphone.
Hello, Monica.
Yes.
Good morning. Yeah, I have a question regarding your presentation when you presented the device ABI. I was wondering which kind of auditory feedback you use in this case. It was just simple note, and if yes, which was the period or the frequency you have used for this signal?
Thank you for the question. Yes, we decided to use a frequency. It was a 500 Hertz tone. I mean, in terms of, replicated at 4 Hertz, so 4 times per second. This was the basic sound used during the training in individual settings. But in the social settings, we decided to use multiple sounds because it was important for the child to understand which was the other. So, for example, if one child was the dog, the other one was the horse, and the other one was the cat, it was possible for them to listen each other and to understand who was the one or the other and which was his position in space. So for the classical psychophysical experiment, and when possible, we try to maintain the same stimulus, but in other conditions, we prefer to let the children have fun. And so this was also based on the feedbacks from the user-centered design we did.
Thank you.
So does anyone have a question? I also have a question, Monica. Could we replace auditory feedback with ABI by tactile feedback on the hand to locate, to try to control the position of hand of blind people, for instance, something like that?
Yeah, I have now, I've been awarded with an ERC project. Within the ERC project, I have this idea of combining audition plus touch in a new device. I think that just touch is not enough because audition is providing a sensory information that is in the space, while touch, as also Olivier showed, is still on the body. So it is difficult for the blind child to link the tactile feedback on space. While I think that ABI is working because it is providing a sensory feedback that may be more allocentric, more on space than the proprioceptive one. But I think that also the combination between touch and audition can be useful if mediated by different mechanisms. I'm trying to test this in this project, and I will let you know in the next few years.
Okay, thank you very much, Monica. We can move on to the next presentation from Eric Vezzoli from Haptics and GoTouch VR, who are companies. So it's our pleasure to welcome you, Eric.
Hello, thank you. Welcome everyone. I'm Eric here from Haptics. Let me know if my screen looks good and we can start. So thanks a lot for this. I invite everyone that might have a question to share it directly into the chat, or of course to pose it at the end of the discussion. So will be a bit different presentation compared to the previous one. It will be a bit more technical, but at the end of the presentation we will see how the technology that I'll share and the infrastructure that software infrastructure that I share is helping academic deliver research studies with haptics in a multisensory environment. So bear with me, it will be a bit more technical, but at the end, the advantages for the research studies will be kind of clear. So the focus of this presentation will be mostly around haptic rendering and haptic rendering processes in technological environment, and how this can play a positive role into the research about haptics, but specifically into multisensory integration. So as most of you are aware, haptics is getting a bit more ubiquitous around the world, specifically wideband haptics, or at least more expressive actuators are getting more and more implemented into smartphones and console like PlayStation 5. And there is also a certain trends over the multiplication of the actuator. PlayStation had 2 before, right now they have 4. They're starting to appear the first smartphone with a stereo haptics actuators and also wearable haptics. We are moving towards having multiple actuators on the body. And this is an extremely fascinating market, because it's evolving really fast. And but there is a set of challenges that are associated with this fast-growing ecosystem. And the challenges is that, as every one of you probably who ever built anything with haptics realizes, that it's extremely time-consuming building everything with haptics, not just hardware, but also building software for it. For a simple reason that there is not really a lot of interchangeable technologies that allows something that you built for a devices 5 years ago to be reused with today's device, let's say. And this generates on the market a bit of a slower adoption of the technologies. On the market, always there is a question is why haptics is not at the level of audio vision. There is a ton of reasons. One of them is also that it's really expensive to be implemented. But we are seeing also that in the academic world, as soon as we can deliver better tools and easier and faster tools to academics, the research ideas actually pop and get implemented extremely fast. So this is a bit of the problems that in interhaptics we are addressing, specifically on the haptic design and rendering part, which is how can we create a framework that allows who's interested to build around haptics in any kind of digital technology to having a shared, unique way to build haptic solution and to deploy haptic solution. So this is a bit the challenge that in interhaptics we are addressing, and in the next few minutes we'll go through how we address this challenge, and how we address it is helping solve some of the issues on the market. So what we do exactly in interhaptics, we built fundamentally a set of tools and software that allows to create haptics in a low-code, no-code way without losing the opportunity to have a wideband haptics, nor the ability to have multiple actuators on your body, nor the ability to include the spatial haptics like texture, stiffnesses, and whatnot. And we packaged this set of tools and technology into segmented for technology groups like mobiles or mixed reality and whatnot. But fundamentally, we built 3 tools that are really great for haptics. So one is the Composer, which is a graphical user interface to design haptics. We have a set of applications that allow you to test in real time what you do in the phones, and some Unity plugins that helps you to build virtual reality interactions. But these are just the means for an end. I would like to spend some word over the technology stack, specifically the haptics technology stack, to clarify what we do and what we are doing to address this unique, or at least a shared way to create haptics for multiple platforms and multiple also technologies. This is also one of the challenges that we are facing, of course. So if you look at the technology stack, you actually start, you can start even with the documentation, which is how actually someone that wants to build haptics should do it. And you go down till the hardware level. What we do with Interhaptics, we do everything. We start from documentation down to the API level, which means that after us, we usually plug into the communication protocol with the haptics device. On the documentation side, we try to share as much as possible how haptics, how you can approach the development of haptics. We are involved in multiple activities like the Haptics Club. Some of the speakers are even here in the conference right now. Tutorials and Udemy courses and whatnot, because we understand that just outside academia, there is a huge gap of knowledge about haptics. Really, there is a huge wall between academia and market about the understanding of what haptics can do. And it's extremely hard for someone which is not a specialist to acquire the basics understanding of how haptics should be done, to be able to implement it into their own pipeline of research. And we'll see that later, and also pipeline of business. But this is another topic, not for this conference. So the documentation is one. On the design side, we published 1 year ago, 1.5 years ago, the first Haptic Composer, which is a graphical user interface to design haptics, not just vibrotactile, but it's also you can design spatial texture as well as stiffnesses, so force responses. And after 1.5 years of feedback also from academics, user as well as market users, we are releasing in September the second version, which allows a dramatically more fluid design process for creating haptics effects, both in space and time. So this is important. So you manage textures as well as managing vibrotactile signals. And these are new Haptic Composer too. We are continuously iterating with haptic designers expert to be sure that it's a transparent tool that allows the creativity for who has to design haptics to do it in a really efficient way. Because as soon as you start hindering the creativity part, the ability to create original works or original ideas actually hinders down, and that's terrible on the creation side. But I would like to spend some words more over the step under it. So this is a design system that what it does, it encodes the haptic signal into a digital form, and specifically it encodes it into an asset. And this asset is where part of our expertise lies. Is we extracted kind of how, let's say, 90% of the haptics technology on the market, or at least available, kind of works today. So including ERM, LRAs, wideband actuator, friction modulation devices, force feedback devices. Basically, what has a market right now, and we try to find an encoding of haptics perception that makes sense, digital haptics perception that makes sense, to allowing through that tool to encode this haptics perception and be able to deploy them on this technology, passing through a unique pipe without having to create a development pipe for each one of them. And fundamentally, we laid that down on 4 perception here, so 2 in space. We can call them textures, so periodic patterns in space, both in 2D and 3D and in 1D, and the stiffnesses, which is compliances, and in time, of course, vibrotactile, and potentially also in the future, heat transfer signal with temperature. So this is a digital encoding of haptics that comes directly from this design system. And for then the next step, of course, is taking these assets and being able to deploy them on the haptic screen, which is nothing else than the human body, right? So we perceive with the human body, so the way that we transmit haptics tactile signal to user is through the human body. So our haptic screen is the human body, or at least this is how we conceive it. And in that way, the haptic encoding that we saw before we can render it and deploy it in multi-tracks and multi-endpoints and mix it in real time, thanks to our rendering system on any body part of the human body if it exists an actuator. And also, of course, it responds, if you're working in VR, it responds to multiple haptic generation events that can be collisions, can be interaction-based systems, it can be basically whatever you can think about it. So it's an extremely flexible system that allows to manage multiple actuators in real time, multiple endpoints. You can make a group rendering and you can make collision-based rendering, as I mentioned, interaction-based rendering. So this is a systems that allow an extreme flexibility to implement a different haptics device within the same software framework. Thus, it allows to spend much less time on technology and instead focusing on the use cases. We are extremely involved in one thing that is going on right now. It's fundamentally the impaired haptic standardization process that is going on. Actually, tomorrow is the deadline for how these digital haptics encoding will be standardized in the future, like in MP3 for sound. This is going on, and there is very implicated to that to share a little bit of our vision. But fundamentally, after defining this asset system and how it's deployed on the human body, the proper rendering system, it's a common process that interprets this haptic material, which is this encoded haptic, encoded digital haptic sensation, and by acquiring the positioning of the body part of the human body, it can be a hand, a finger, or whatever you want for any kind of tracking systems and the processor clock, allows to render the haptic feeling, but through some trickery that or some algorithms that he had to build to be able to fundamentally do simple things. Acquisition of a position is between 30 and 120 Hertz in commercial systems. Haptics perception is 1000, so there is a clear undersampling problem there. So we built some behavioral model, haptics behavioral model that allow us to model how the haptics perception evolves when the user is moving their finger and hands, even if there is undersampled, thus being able to create an haptic buffer out of this, if we think about spatial haptics, that is able to go up to 8 kilohertz rendering, thus having a extremely wide-band signal, even with a not extremely qualitative tracking system. And then this rendering that is still unique till now, just at that moment, becomes separated in any kind in the specific actuator and device logic. So at this moment, we take into consideration, is this an LRA, is this an ERM, is this a wideband, or is this a force feedback system? But everything we discussed till now is something that it's independent from the haptic technology. So why is interesting? It's interesting because if you need to consider a new device here, you want to make a study with multiple haptics devices on the human body, it's your implementation pipeline, it's extremely rapid, so because it's common. And you can then basically create the interface layer, which is translates your like 0 dB render device to the machine language just at that moment. So basically it simplifies and abstracts all the complexity to create an efficient machine to build the haptic rendering. And what we have today, I mean, we have basically compatible with more than 15, 20, I don't remember how many haptics devices on the market right now. But specifically, what we see that from an academic point of view, our partners love it is that you can build the integration of your own haptics device extremely fast. So it takes you less than 1 week. You can basically implement any kind of haptics device with any kind of number of actuators directly in the engine. And being able to leverage all this pipeline of technologies to focus on your use case, focus on your implementation, and forget about software complexity. Okay, as soon as you have a device that can communicate with a PC or a smartphone or even an iPhone, because we are compatible with all of that. Basically, you build this interface, the translation layer here, And basically you can implement any kind of numbers of device, because we have already managed more than 100 actuators at the same time. And it's extremely transparent, both for the implementer and for the user, because the engine allows this segmentation of the haptics complexity, and especially the management of changing of kind of perception, changing of kind of actuators, and all of that can be simply programmed into this custom interface. And let's go then to the, okay, I shared a lot of how we do stuff that might be interesting or not, but the question is how these things can help a research process, and what we are doing right now to help the research process, because we have multiple collaboration in place, this one with Multitouch, of course, but also with other universities. One that I want to talk about, and I think it's kind of interesting, it's also touched quite a lot the multisensory, but specifically practical application of haptics, is that we are running a study with Leonardo, which is an Italian aerospace company, and also Politecnico di Torino. And in this case, we're talking about virtual reality training. And probably you're aware that the virtual reality training market is kind of taking off right now, because there is a huge benefit from businesses. And there's been a lot of speculation how haptics can be beneficial for this process. And there are some studies that shows that maybe it is, maybe it's not. But the real question is, what haptics? In which kind of haptics? To which degrees, and how can we compare? Because what it is important is that the implementation system needs to be the same to be a very consistent interaction, as well as haptics feedback scenario, and the solution behave exactly the same to be able to do systematic work to understand how haptics impact, for example, this kind of activity. And here we are running this study where we are comparing 5 different interaction systems, and 4 of them has haptics, and 1 is a hand tracking system. So the basic controller of the Oculus Quest, a hand tracking system, and 3 haptics gloves with actuator placement on different places. So manus having the back of the finger, the viewable sensor on the tip of the finger, and the third one is the sensor glove that has both a tactile actuator and force feedback. So that due to the fact that the implementation is the same for all of these devices, it allows to create a systematic studies onto when and how haptics technology helps, and if it does help, what actually you need to have a beneficial effect on practical use cases. So in this direction, really, we are in virtual reality training. So we have in virtual reality, so this is completely multisensory. It's a completely multisensory environment. But thanks to this stack of technology, we are able to collaborate with the university to empower them, and we are also involved in the studies to quantify the benefits of haptics in a real world environment. In a real case that can have directly business impact tomorrow. Otherwise, what would have needed to be done is to rebuild 5 times the same systems, which is, as you can imagine, not time effective, cost effective. So would have taken maybe even years to build this kind of system. But this is one of the activities. Second one I want to share is, and then I would close the presentation, is again, due to the fact that we simplify and abstract the complexity of haptics, at least from implementation level, we are collaborating with business schools that would like to understand, for example, in this case, the impact of modulated haptic feeling and design haptic feeling into e-commerce applications, both in augmented reality and in standard e-commerce experiences, in a context of multisensory stimulus. Because in this case, we are both studying the impact of haptics and sound over the perception of, over the willingness of the users to purchase a digital item. Specifically, the objective here is to understand and quantify. The importance here is quantify the impact that haptics might have onto the willingness to purchase. Because even if you are able to quantify the increasing of 2% of that, which is massive, it has direct impact to the opportunity to the increase of the effectiveness of e-commerce application for businesses. And this, we can do it because we have a design system that allowed business school people to build refined haptics experiences to enable them to create these studies. So these are two ways that we love to collaborate with universities to simplify the research activities thanks to this technological stack. And what we learn how results, of course, but we are in a continuous optimization process for our product, which we want to make it better. And in this direction, we are extremely open to collaborating with research institutions also for project writing and whatnot. So these are two examples that I wanted to share. So I'll kind of close here, so I don't. We are already late with the webinar. So we are really ready to collaborate with academics. We have a really flexible licensing model that allows fundamentally research institutions to do what they want with our product. You can customize completely our translation layer to build any kind of any number of any kind of haptics technology that you would like to build on it to simplify your implementation stack. And I copied to time the same rectangle there. And do not hesitate to, frankly, really to reach out to me or to the company if you are interested to anything which is implementation of haptics in digital environments and you want to get away from the complexity of building software. And I close here the presentation. Please, if you have any question, I would be really happy to answer.
Okay, thank you, Eric. So it was a good overview of the challenges about introducing more multimodal, multisensory stimulation into human-computer interfaces. So we have a question by Rania Hassen. Okay, so you can now talk.
Hello, hi, Eric. Thank you for the presentation. Very nice overview of the work that you've done. I'm just wondering about the rendering engine, or you call it InterHaptics engine. I guess it's in page 15 or something close to that. Would you elaborate more about how you managed to interface with different hardwares and different actuators, and if you also would be able to drive drive basically piezo or LRAs or different types also of HD kind of haptics?
So thanks for the question. We could stay here half an hour to discuss about this. So you can continue offline if you're interested. So the system is simple. The simple is built on few assumptions. And as you know, Piezo, for example, implement displacement and wideband actuator. I mean, you have certain clusters of actuators that behave in a similar way. Let's say piezos behave in a perceptual level really similarly as wideband actuators like voice coils. LRAs, if you modulate them on the frequency modulation frequency, on the resonance frequencies, you can control them in amplitude. So somehow you can cluster them together with ERMs, which you can modulate them just in amplitude. So if you do a high-level clustering of these different technologies, including force feedback and microkinesthetic and even friction modulation, you will see how the driving signal for each one of them can be merged together in a way that you can build a haptic encoding where you always have all the information that you require to drive all the families of actuators that you need, okay? And selectively, when you know which haptics hardware you have, you can go and extract from your digital encoding system the information that you require for that, okay? So in that way, and the specific device-specific adaptation, you can build them in your device-specific interface where you can go and adapt, for example, if you need a specific filter for that device, you need a specific frequency response, or it has a specific idiosyncrasies that you need to take into consideration. You can take your, let's say, digital encoding that has this multi-level representation of a haptic signal that you can selectively extract, and then you can adapt your driving signal to the device-specific system in the device-specific interface. So in that way, you are able, for example, we have example with the sensor globe that has one wide wavelength actuator, 5 ERMs and 5 force feedback systems, and all of them are driven in the same way. Because we selectively take out from the encoding system what we need to drive the actuator. Did I answer to your question?
Yeah, sort of. So let me interpret that in a different way. So you basically create a database of different high-level encodings for each device specific, and then in deployment time, maybe, or maybe, I'm not sure if this could happen in real time, you basically selected the appropriate encoding for the hardware that you have. Is this correct?
No, not really. So,
not really?
No, apologies. Maybe I'm missing time. So everything is everything is real time. Okay, nothing is precompiled here. So everything you see here happens at every application frame. So the computation is real time. There is no precompiled tables, and there is no influence of the device. So the devices are a display, so they execute your signal, right? It's just the way that we encode our signals. Okay, you can encode it in PCM and having a wideband signal, right? But you cannot do anything with that PCM signals if you have a system which is driven through amplitude, right? Because you simply don't have the information. But what we did is that we encoded this wideband signal in a way that allow us to extract the parameters of the information that we need to drive, let's say, an amplitude-driven signal, separated from all the other information that we require to drive, for example, a wideband signal. So that the encoding is the same. It's just the richness of the information that we extract that is adapted to the kind of actuators that you have. Okay, so there is no
something similar to the AHAP, right?
It's a bit more developed than the AHAP, but the concept for vibration, for example, it can be compared. So there is a bit more things that you can build out of it, but it's kind of similar in concept of that one. That HAP is one frequency and one amplitude, right? So explode that in 16 harmonics that you can build as you want, and in 4 different perception, including forces and spatial systems. And in that way, basically, you can extract the information that you require.
Okay, maybe you could continue this discussion during the break session. I think that there is a link where we can have social interaction. Before that, we have a question from an anonymous attendee about who thank you for the presentation, and he wants to ask how could characteristics of human tactile perception, like mechanoreceptor properties, can be integrated or considered in the design stack when designing haptic experiences. So it's in the Q&A section of the Zoom.
This is a wonderful question, and thanks for posing it. And we faced this question the last month specifically when thinking about the standardization process of MPEG, and I think Frédéric, I gave you a presentation for this some time ago. So it's really great question. So there is on our, at least on our understanding, of course, that will be challenged, and it's fine. There are different frequency range where the human tactile perception is different, right? So we have the 70, 80 Hertz, the Pacinians take over, and under that you have a predominance of the other mechanoreceptors slowly adapting. And what's the catch? The catch is that they actually work in different way, right? But if you see everything which is vibrotactile, for example, we take there was a HAP example of Apple before. It works between 65 and 300 Hertz. So is basically just in the Passinian range. So it's a unique way to build, unique way to perceive haptics, right? But if you expand the expressivity of your actuators down from 70 to 0, it's definitely a great idea, the fact that the way that you should design your haptics experiences should be different, because the way that you perceive haptics is different. And this is true. We see that because in our haptic composer, we have 3 modality of design. We have the kind of force feedback design, which is meant to be it's a force profile. It's meant to be low frequency. And you actually design it in a different way. And you approach the design in a different way. So it's definitely true that probably there should be different design guidelines for a different frequency perception band that the user have. And I hope that, but I can't really tell you more than this, because this is a great question. And if you're interested to explore it, we can discuss. I don't have answers. I'm curious about the answer about that question.
Okay, so Eric, so thank you. So we thank the speakers for this first session. We may have a break now. We scheduled a 15 minutes break. We are running late, so we go back in 15 minutes, and you can put comments in the chat window if you want. So so maybe we can make a photo of all the participants who are here now. So Rania, sorry. Okay, so maybe you could switch on the cameras. Okay. Thank you, Nitzan.
Mihail also.
You have it? We have one Mihail, we have 2 Mihail.
I don't see one of Mihail's. Okay,
No.
I'm taking the photo.
Okay. So we start the next session with the presentation by Dadian Brahimai from University of Lille, which is another presentation about technical issues. So maybe Dadian, you can share your screen and start your presentation.
Yes. Can you see my presentation?
It's not full, now it's full screen. So yes.
Okay, perfect. So good morning, good afternoon to everybody. I am Dadian Brahimai. I'm a PhD student of the University of Lille, and I'm also involved in the multi-touch project that Frédéric have presented before. So today I'm going to talk about technological issue with multimodal touch input device. We are going to start with an introduction about multimodality, and then we are going to have a look about the available technologies, especially for haptics, with some examples. So the first question we are going to ask ourselves is, what is a multimodal touch input device? The most simple answer we can give is that it is a combination of haptic feedback with one or more modality. So taking into consideration haptic feedback, we can have visual or auditory, and we can consider also the condition of bimodal, visual haptic, or haptic auditory, or the trimodal condition. Taking in consideration these modalities, the typical hardware used for in order to display this kind of stimuli, for visual, for example, we can have screens, projector, augmented reality glasses or 3D glasses, virtual reality hand-mounted devices, or peripheral lights. And for what regard auditory, we have like speakers or headphones. And we are going to make a focus on haptics technology on the other slides. So how multimodality works? If we start considering, for example, the stimuli, we can have different kind of stimuli. In this case, I'm considering the multimodal condition. The stimuli are then received and by our receptors, such as, for example, mechanoreceptor for the tactile feedback, and they meet in one point that we called convergence. That is exactly the moment where the information coming from different stimuli meets all together. Then this process is then moved on our brain when we have a multisensory processing, that is the integration of this information. And we can end with an experience evaluation where people usually try to define this kind of multimodal experience with different layers, such can be perceptual, aesthetic, meaning, or emotional. The most advanced multimodal interfaces that we can consider are considered to be the fusion-based one that co-process two or more combined user input modes that can be entered simultaneously, such as, for example, speech and touch together. Usually these interfaces have been designed and optimized to support a specific range of tasks. And also some multimodal interfaces actually can be considered multimodal and multisensor one. This interface combines multimodal user input with one or more forms or more forms of sensor control involving contextual cues. For example, proximity of our cell phone to the user's ears may turn it on or off. Another category that we can consider are the temporally cascade. These multimodal interfaces process a combination of modalities that tend to be sequential in a particular order, such as, for example, gaze direction at an object followed by a speech about it or touching a related element on a flat surface. System of this type potentially could process meaningful information also trimodally, such as, for example, user gaze, the touch or pointing on a certain point followed by a speech. So in this context, we can see, for example, the three kind of feedback related with the user and the three blocks that are responsible for the visual rendering, the physical rendering, and the audio synthesis. And all these blocks are usually handled by a system. The typical approach that can be used for the system can be, for example, two kinds. The first one is considered to be a single model. Here, scenes are often distributed into separate computational process for each modality. Such, for example, we can have different rendering rates. However, it does pose the problem of defining mapping and controlling the relationship between the process. If the correlation between different modality is not sufficiently explicit, the sensation of believability and presence of the virtual object, for example, may suffer of this. Another approach that we can see is the distributed approach. This is an alternative way of designing multimodal scenes, and is to model them with a single formalism. Indeed, the physical modeling allows to create scenes of deformable objects that can exhibit visual, mechanical, and acoustic behavior. Indeed, the object that we touch is the one we see and we hear. This approach can also be seen or referred as a multisensory one, and usually tends to guarantee coherence between the different modalities. So now let's take a look on the viable technologies, and we can start by making an haptic classification. The most simple classification we can do, it's called the 3S of haptics, in which we define haptics through shape, substance, and surface. If we want to have a better classification, we can try to classify haptics depending on the actuation that the device is using. We can have, for example, in this case, 3 categories related with mechanical vibration, surface shape changing, and friction modulation. Starting from the mechanical vibration, we can have, for example, eccentric rotating mass when we have frequency and amplitude that are dependent. We can have linear resonator actuators that are resonating at a certain frequency due to a spring and a mechanic mass. This makes amplitude modulation very easy, but we have to consider also that in this case, we have only one resonant frequency. Then we can have, for example, piezoelectric actuators that we can make vibrate by properly controlling the voltage input of the actuator, or voice coil. In this case, it provides the motive force to the cone by reaction of a magnetic field to the current passing through it. And controlling the current, we can control the vibration of the actuator. Taking a look at the second group that are surface shape changing, we can have, for example, pin array. These systems are more complex with the first one. The pin array are composed, is an array composed by pins, and by properly controlling the pins, it is possible to release a tactile feedback, and it is also possible to render shapes on the changing surface. And we can have, for example, electrode array, when these are which can directly stimulate the human nerve in order to produce a tactile sensation by an electric signal, or pneumatic chamber. For example, this device that you can see here is made by Harrison and Hudson. They developed the tactile feedback device actuated by pneumatic chamber, which can fill air into the customized design air button. Then we can move on to the third group, that is friction modulation. We can have devices that are using the technique of ultrasonic vibration. In this technique, when a finger is sliding on a vibrating plate, we will have as a result a reduction of friction. In particular, the friction decreases as the signal amplitude increases. And the contact force between a finger and the device surface is altered by changing the friction coefficient through modulating the frequency and intensity of a vibration stimuli that simulates textures. The other technique for friction modulation is due to electrostatic effect. Here, tactile feedback device based on this effect creates a capacitance between the finger and the electrode of the tactile device. The user's finger can perceive electrostatic friction force under the action of excitation signal that apply to the electrode, and the tactile sensation is exhibited by changing the frictional force. Now I would like to see with you a few examples that are using this kind of actuators. The first one is a multimodal in-vehicle interactive system. Here, the author want to solve in such a way the problem of doing a secondary task while driving that usually is considered not safe. In order to solve this problem, they propose a multimodal device. In this case, we have Haptic. They are using an EMR actuators, and they exhibit different vibration stimuli based on position or gesture. As you can see here, they have a different intensity that go from weak, medium, and strong, and they combine these three different intensity in order to produce different tactile feedback. They have also an auditory system that is used to confirm completion or gesture or to give additional information. And for the visual feedback, as you can see, they are using a classical tablet. The authors here, they performed an experiment with 5 trials, considering different conditions from unimodal with only vision, bimodal, or multimodal in driving and not driving scenario. Here, the driving simulation, the experiment consists in a driving simulation while completing a secondary task on the tablet itself. From their results, they looked on the accuracy, completion time, lane deviation, last time of the road, and the perception questionnaire. From the result, we can see that there was no significant difference between trials in terms of the accuracy and completion time and for lane deviation, but they found a significant difference in last time of the road, especially from trial 1 and 4. So from trial 1, that is considered to be the unimodal, only vision, and trial 4, that is the multimodal condition. Furthermore, through a perception questionnaire, they also highlighted how multimodal was rated more with respect to all the other conditions, so unimodal or bimodal. So as a final result, we can see that completing a secondary task with this multimodal touchscreen could not have influence on the driving efficiency or safety, but still improve the user experience. Moving on another example, this one is called Haptable, and is a multimodal visual haptic system. We can have a picture of the system here, and in order to make it a bit simple, we can say that there are 3 main modules. The first module is related with gesture detection. The second one is related with the visual display that is created through a projector that creates the visual feedback, and the haptic feedback. In this case, the haptic feedback is it's provided not just by one unique actuator, but they use 2 different methods. One for static gesture, using electromechanical piezoelectric actuators that vibrate, and the other one for dynamic gesture, they use electrostatic actuation. They then performed 2 different experiments in order to validate the device itself. One for reverse tactile flow, when the user was allowed to put 2 fingers in the screen, and using different intensity, they was trying to create a illusion of a flow from one point to the other of the finger. And the second one that is related with a haptic node. Taking a look a deeper view on the haptic system itself, for what's related with piezoelectric actuator and for static gesture, they use vibration maps. They first construct this vibration map on the tabletop surface in advance, and then they use it to display haptic feedback to the user in real time. They created in particular 3 different vibration maps, one related with displacement, one with frequency, and one with actuated piezo pads. For what regard the dynamic gesture, as I said before, they are using electrostatic force. In particular, for the knob, they use different sectors. They divided the knob in different sectors and mapped it on the menu. They're using different signals. They tried different haptic feedback. In particular, they try to put haptic dentent at the sector crossing of the haptic knob, haptic dentent at the crossing section plus constant friction inside the sector, or using a velocity-based friction inside its sector itself. As a result, adding haptic feedback improved interaction quality, user experience, and also the confidence of the user, but not the efficiency or competition time for what regard the experiment itself. Here, the advantage of this kind of system is that different haptic stimuli are used on a transparent surface, while limitation of this system can be the fact that piezo patches produces audible noise when the finger is interacting with the surface itself. Moving on, we can see another category of available technology for haptic that are called contactless haptic technology. We can divide this contactless haptic technology into big group. The first one is related to what I called here air-based, because the tactile stimuli is produced thanks to the air. We can have, for example, controlled air stream. Here, inherent latency. We have inherent latency due to the vortex traveling through air. You can see the vortex here produced by this device. And also we don't have the possibility to have continuous sensation using this kind of technology. And another limitation related with this technology is that they have a quite coarse spatial resolution. We're talking about something about 8 centimeters. Moving on the other technology, we can use, for example, subbuffer in order to have a contactless haptic. We list these methods as limited control over the spatial resolution of tactile sensation. It can produce relatively strong and continuous forces. Taking a look on the other kind of contactless haptics, we can have, for example, laser and electric hearts, where the tactile and thermal effect, we can have a good tactile and thermal effect with a high spatial resolution, while this limitation of this technology is the limited range. You have to be really close to the device itself. Or we can use, for example, electromagnetic field in order to have contactless haptics. As the same for laser and electric hearts, here we have a limited range, but another limitation of the technology is the fact that it is necessary to wear on the hand magnetic implements or use magnetic gel or wax in order to perceive the tactile stimuli. As last that I've left here is ultrasound array. I left as the last one because it's quite spreading quite a lot in this year in the scientific community and the research. And this kind of device is based on the principle that using an array of ultrasound actuator, it is possible to produce different and well-controlled audio signal that can focalize, creating what it is called a focal point. And through this focal point is then possible to have a tactile stimulation of the hand, for example. But this technology also have different limitations. Such as, for example, precision. Indeed, we can have grating lobes, as you can see from these two images. And from the lateral side, we can see that the focal point is not exactly a point, it's more ellipsoids. Then we have also limitation for what regard the strength and perception. Indeed, the typically perceived force with this device is around 16 millinewton. And also the other limitation is that the force that we can produce through the device is proportional to the number of transducer itself. Another limitation that we can see is, for example, the range. Here we're talking, we can use the device up to 40 to 50 centimeters, but it is not possible to be more far from the device itself. Other limitation can be size, weight, cost, power consumption, and heat dissipation, for example. And also noise. Indeed, modulating the signal, the ultrasound signal with in a low frequency that is audible, produce noise, creating the effect or the multimodal experience may suffer for this limitation that we can see here. I would like now to see a few examples with you that use this technology. First one that we are going to see is a floating virtual screen. Here we have 4 main components. As we can see from the schematics, we have an LCD here and an aerial imaging plate. The aerial imaging plate is used for 2 reasons. The first one is in order to project the image of the LCD in air, making the floating virtual screen. And the other reason is in order to use ultrasound phase array by reflection. In this way, it is possible to reflect the ultrasound waves on the aerial imaging plate in order to produce the tactile sensation in mid-air. And finally, we can see an image of the complete device here. This kind of system, it's simple in terms of controlling it. They're simply using a PC to control the system itself. And we can have an idea of how it's working from what regard the sound pressure in different points of the device itself. And making a zoom in the white square that you can see here, it is possible to have a better representation of the focal point. And as I said before, it's not completely a point, and the shape is also not circular, completely circular, making a bit difficult to choose where exactly to give the haptic stimuli. The authors then used 3 different applications in order to show the usability of the device. And an interesting part of this work is that here, haptic represents a crucial feedback for the system itself. Indeed, without haptic, the user does not know where they have to stop with the touch input. Indeed, they can go far inside the screen itself. And so using the illusion of the floating screen. Another limitation of the technology of this device is also the aerial imaging plate itself. Indeed, it has a narrow angle view, and moving on the left and on the right of the device itself, it will result in a distortion of the image. Furthermore, the last limitation that we can see in this device is that the way they are performing, they're using the ultrasound array is through modulating the ultrasound signal in a lower frequency, but this produces also a less perceived stimuli itself. The second example I want to see with you is mid-air gesture interaction in car. Here we have the haptic system with a different gesture. We have different haptic feedback depending on the gesture itself. They're using also auditory feedback. Indeed, they are associated some gesture with the notes with a short duration. And they're using for the visual feedback the monitor, the blue monitor that you can see in the image, and also a LED strip. This is the use of peripheral lights. And the interesting part of peripheral lights is that they are not going to put too much load on the user itself, because the user doesn't need to focus on the peripheral lights in order to have this information. Then they performed an experiment considering 5 conditions, 2 unimodal with visual and ultrasound, and 3 with bimodal, visual ultrasound, auditory ultrasound, and ultrasound and peripheral lights. The experiment consists in changing lane while they're performing a secondary task that was considered to be the gesture itself, and the structure was given by speech. Taking a look on the result, we can see, for example, the out of the road time, eye off the road time. They were found that here the highest score was given for visual and ultrasound together, but there was not found no significant influence of car duration and number of glances on lane deviation, and also no significant difference for what regard the gaze duration and the secondary task performance itself. Taking a look also on the lane deviation and the result, we can see that also here there was no found significant influence on the condition of the lane deviation, and no statistical significant difference in the lane deviation across the different gestures that they have developed. Taking a look also on the gesture performances, we can see that they strongly, at least for the article, we can see that they strongly depends on the feedback type that the author themselves decided to use for different gesture. One of the gesture that you can see that is the highest one was the V gesture, was the user have to perform a V gesture over the ultrasound array and receiving just a feedback on one finger in order to turn on or turn off the entire system. We can also take a look on the secondary task performance, for example, and as you can see, ultrasound feedback here resulted in a really low correct gesture performances, significantly worse with respect to the other condition. But anyway, the addition of ultrasound with another modality bring a higher correction rate for what regard the secondary task performances. In order to try to summarize all this information, we can say that adding haptic feedback can reduce cognitive load when we interact with a multimodal system, but can also improve interaction quality, user experience, and also confidence of the user itself. We saw that still some technological limitation exists. Indeed, as we saw, users' finger interaction with an haptic feedback can produce audible noise in certain systems, especially when we talk about surface haptics. So when we're talking about flat surfaces. Moreover, multimodality integration also in human is to be considered and taken into account when we are making the design of the system. Other limitations are also related with temporary issues, such as the synchronization of the different signals coming from different modality, or the handling all the signal in a sequential way. Indeed, to find out the best multimodal input for a multimodal system still remain an open research question. Thank you for your attention. And if you have any question, I will be happy to answer them. I'm going to leave also my contact so you can write to me.
So thank you. Thank you, Dadion, for your presentation. Maybe we have a question in the from the attendees. So you can raise your hand and or use the Q&A section. So Dadion, could you maybe precise more a bit about what is sequential between synchronization of the multimodal stimulation?
Sure, the point of multimodality is that we have to handle different signals and different information all together. And the knowledge about how we process the information in our brain is quite essential in order to handle this information temporally. So we can have situation in which multimodality is represented by synchronization of all the signals, such as, for example, when we see a rock that is falling, we see the rock touching the earth, but we also hear the sound contemporarily, for example. Or we can have situation in which it is important to handle all these different information in a sequential order, because they have a meaning only if they are sequential. And so if we synchronize, for example, in certain situation, these signals, this may bring to a not realistic sensation, and so ruin the fact that we are receiving all this information and is not more filled as multimodal. You're muted.
We can move on to the next presentation. Thank you, Dadion. The next presentation is made by Radu-Daniel Vatavu, who cannot make it today, so he sent his presentation by video.
Hello, my name is Radu-Daniel Vatavu, and I am a professor of computer science at the University of Suceava. In this talk, I will discuss about our research interest in gesture-based input with interactive computing systems, devices and applications, and I will present some of our prior work regarding combined haptics and gesture interaction. The second presenter is Mihail Terente. He is a PhD student in our lab at the University of Suceava and an early stage researcher in the multi-touch Marie Curie ITN action. In the Machine Intelligence and Information Visualization Laboratory, we are interested in the design, development, and evaluation of new artificial intelligence and information visualization technology to support innovative and rich interaction between humans, computers, and environments in order to advance knowledge in human-computer interaction and ambient intelligence. As part of this goal, we are interested in techniques for human-computer interaction, such as touch, freehand, and whole-body gesture input. We prototype new interactive techniques for smart mobile devices and wearables. We design new user experiences for smart environments, prototype for home entertainment and interactive television, and explore various concepts regarding ambient media in smart environments. During these explorations, we have also considered haptic feedback in the form of vibrotactile patterns, useful in order to guide gesture input and to enhance user experience with gesture input. In this talk, I will focus on some of our prior results that we obtained in our laboratory regarding user perception of vibrotactile feedback during gesture articulation and user preference for vibrotactile feedback patterns delivered by a wearable device designed for the finger and palm augmentation. Regarding the first topic, I'll present results from an experiment involving various gestures and various vibrotactile patterns delivered to the arm. Regarding the second topic, I'll present results from an end-user elicitation study where the participants invented vibrotactile patterns for a wearable device for the index finger and the palm of the hand. We conducted an experiment to understand users' perceptions of vibrotactile feedback at arm level for various interaction contexts involving touch and mid-air gestures. 11 participants volunteered for our experiment, and none had previous experience with vibrotactile or haptic-based interaction. For this experiment, we developed a wearable vibrotactile device with actuators powered by a control unit attached to the arm near the wrist with 2 precision microdrive motors. We considered 5 different vibrotactile patterns, 3 gesture types, and we also varied the intensity of the vibrations delivered by these devices. We are interested in this study in understanding users' capabilities to recognize vibrotactile patterns applied at arm level, as well as the intensities of these patterns. Overall, our participants were successful at recognizing combined vibrotactile patterns and intensities in only 55% of all of the trials. Although this overall accuracy performance is modest, individual accuracy rates computed per pattern and intensity levels were significantly higher than the overall performance, with 79.7 and 67.8% respectively. These results show that our participants managed to recognize either the vibrotactile pattern or its intensity with acceptable rates, but their overall judgment of the multiple characteristics of the vibrotactile stimuli failed significantly more often. Based on these findings, we recommended a number of 4 easy-to-apply guidelines for designing vibrotactile feedback to be delivered by an accessory wearable device at arm level during touch and mid-air gesture input with another device. To find out more about our results, experiment design, and these recommendations, please see our Interact paper from 2015. In a second experiment, we wanted to understand people's perceptions of a new concept called the digital vibram, as well as their experience interacting with digital vibrams implemented in our new prototype. Digital vibrams represent manifestations of digital objects in the physical world in the form of vibrations. For instance, when picked up and lifted off of the screen, a digital object such as a picture on a smartphone turns into an invisible, zero-weight digital vibram that produces vibrations on the user's finger or hand. While in the physical world, digital vibrams can be transferred to other locations, such as the other hand, or they can be placed inside physical containers, such as a box, until they are picked up again and placed on the original device, where they resume their visual representation on the screen. Digital vibrams are invisible to the eye, have zero weight, yet are detectable by means of localized vibrations on the user's hand or finger. We designed a prototype consisting of 3 types of hardware and software components that can be worn by the user, attached to physical objects in the environment, or installed on touchscreen smart devices. We conducted a study of 20 participants in order to understand their perceptions of this new concept, as well as their experience interacting with digital vibrance. We also asked our participants to think about vibration patterns that describe well various digital object types commonly found on smartphones, such as images, music files, phone contacts, short paragraphs of text, and others. We then matched these proposals against each other in order to compute agreement rates. Overall, the agreement rates of our participants for vibration patterns for various types of digital objects were small and fell between 0.037 and 0.216 on a scale of 0 to 1. While most of the proposals were simple, consisting of one pulse of variable duration, such as a long pulse, a medium pulse, or a short pulse, other proposals were more elaborate, such as 3 consecutive short pulses to denote a PDF file, combinations of 2 pulses of different durations, such as short-long, short-medium, long-short, etc., or repeated pulses, such as 3 short pulses in a row to denote a music file object. Digital vibrants are invisible digital matter with the capability to transform digital objects from a visual representation into a tactile one. To find out more about this concept, our experiment details its results, but also implications for wearable devices and interacting with invisible zero-way digital matter. Please see our 2016 mobile HCI paper on this topic. Thank you very much for your attention. If you have any questions or feedback, I would love to receive your email and start discussing. We also have other exciting work about gesture interaction, which you can find at these 2 websites. For the rest of this presentation, Mihail Terenti will give you a live demonstration of a web-based tool that we are currently developing in order to enable practitioners and researchers to easily define, save, store, and download custom vibrotactile patterns for their application prototypes involving smartphones, smartwatches, but also other mobile and wearable devices that can deliver users with vibrotactile feedback. Thank you.
Okay, Michael, you can share your screen, please.
I hope you can see my screen.
Yes,
so,
good.
I'm Mihail Terenti, and in this presentation, I will speak about a tool I'm working on. So, one of my objectives is to develop a web-based tool that will enable users to define, visualize, and store vibrotactile patterns for their application for interactive systems. Now, using these tool users can create a vibrotactile pattern by combining a few components. Each component represents a mathematical function that can be defined using the parameters below. Till now, we've added a few functions that have been commonly used, For example, one of them is exponential decay sinusoidal model from a recent paper at UIST by Parker and colleagues. This model is very flexible and enables specification of a variety of signals for vibrotactile pattern. Beside the mathematical functions, we have added free draw options, which allow users to sketch the shape of the signal directly. The final composed signal that will constitute the vibrotactile feedback delivered to the user is approximated as a set of intervals with constant intensity. We believe that this approach is useful because many of the shelf devices, such as phones and smartwatches, do not support continuously varying the intensity of vibration. The tool allow to specify the custom duration of these intervals. Also, this format of the signal will be exported to the and used in application. So the exported file will contain a set of entities described by two parameters, duration and the relative intensity. We decided that to export the final signal as a set of constant intensity entities because almost all standard devices have limitations of how their vibrational system is used. For phones, watches, and wearable devices, we can just turn on and off the device's vibrational system. So in order to play vibrations with variable intensity, we use a library called Haptics.js, which allow simulate different vibration intensities. We are still looking into this library and how it can be useful to our proposal. I have started to explore vibrotactile feedback to augment several actions in a simple game designed by for smartphones. We plan to design and add vibrotactile feedback in a few more applications in order to demonstrate the functionality of the web tool. For example, in the future, an application for smart watches and another application for a smart environment from the laboratory where the user is tracked using a Vicon motion tracker and the specific vibration can be delivered at different spatial locations. I hope this tool will be useful for all developers who want easily to add vibrotactile feedback in their applications. Thank you for your attention.
Thank you, Mirel. Unless you have questions, maybe you could, okay, Milad, you want to ask a question, so go.
Yeah, I was going to ask Mihail, they have developed this program to generate signals simply. And if another developer wants to use these signals in their apps, which they are probably using, developing with different programming language like Python, they also have an API which they can easily import this data into their programs because the format you are saving your signals is kind of new. And the other programs are using different formats. So if developers want to import your data, they need to either have an API which you provide for them, or they should write it themselves. It will be again time consuming.
The exported file right now is a simple JSON. So it can be easily used in languages, so it's a universal format. Now we are developing few applications using JavaScript because it's a widespread language, let's say, and but for Python, for example, you also can use because it's just a JSON file. And,
but it's right that you can use import JSON files, but as I understood, you are saving each signal's intensity and duration.
Yes.
The JSON files, and if you want to use it in your files, probably then you have to convert them and say, okay, this is a signal of sinus with this time and this frequency, and they should be attached together. So again, they have to deal with these things in their apps if you have some APIs ready for them.
Yes, for JavaScript, we use a library, Haptics.js, which allow to, with a few transformations, it's easy to use this format in this library. But for other languages, we haven't checked yet. But I think it could be easy to transform data from this format to other formats.
Thank you.
So we have a question in the Q&A section from George Collignon. So is Vibro accessible online?
Right now, it's not accessible because we are developing it, but it will be available, of course, when we finish it.
Okay, thank you. We could put a link in the.
Actually, we have a developer server, for developer a server, but it's still in development, so it's not stable.
Okay, so thank you, Mirel. So we can move on to the next presentation from Arthur Paté, who is very courageous to end this workshop session today. So maybe can you share your screen?
Yeah, I'm doing it. Can you hear me?
Yes, we can hear you. Everything is perfect. I just mute Mirel.
Yep. So you should see my screen now.
And now it's full screen, so it's good.
Okay. So I guess I shall start now. So
yes.
So I'm going to give you a presentation of an ongoing project. So there's not going to be many results because the analysis is still underway. But it's about visual, audio, and haptic or vibro-tactile interaction in the context of music, music performance, and music perception. So just a few words about us. I need to stop my stopwatch just to be sure I keep it on time. So our team is made of actually two sub-teams coming from two different disciplines. First, so I'm part of the sub-team which is interested in musical acoustics, sound and music perception, vibration perception, and also auditory display. And the other guys in the team, I hope you see my pointer. The other guys in the teams are more in the computer science disciplines, interested in human-computer interaction, but with applications to musical interactions and new musical instruments. So obviously we have something to do together on the topic of musical instruments. Well, so I try to keep it short on the context, but I think it's important so that you can understand our study. And I'm going to give the context from my perspective as an acoustician interested in sound perception. So the context is the main question for us is to study and to understand how instrument players, musicians perceive their own instrument. If you look at the literature, most of the time, researchers tend to reduce music to sound only and to build all their experimental protocols based on listening tests only. I'm not saying everyone does this, but I'm saying this is the main tendency in the literature. But the problem is focusing on sound only and doing only listening tests is kind of poor, because you lose all the other interactions that you can have with any object, but in particular a musical instrument. So in our approach, we're trying to explore the perception of musical instruments through protocols that will, that will preserve the vibrotactile and visual cues for our perception. Well, that's it. So we try to preserve like natural ecological situations for our players and try to keep this multimodal interaction. So that's the broad context. And being a bit more precise on the context, I don't know if you noticed, there is a second author on for this presentation. It's Collignon, who is doing a PhD thesis under my supervision, and his topic is so he's trying in his PhD thesis to identify the contribution of the auditory input and of the vibrotactile input to the global evaluation of musical instrument. So in his way of doing it is to try to say offer to the musician some kind of instrument on which you can control the sound feedback, so the audio feedback and vibrotactile feedback independently from one another, just to be able to study how multimodal integration phenomena occur during musical performance. And that will explain why we're using the electric guitar for our studies, because this instrument is, so I guess you all know what is an electric guitar. That's a guitar that produces sound, but the sound is not heard from the instruments. The instrument is not emitting much of the sound. You hear the sound through the amplifier, but you feel the instrument on the instrument itself. So the vibrotactile feedback is given by the instrument, and the sound feedback is provided by the amplifier. So naturally, like in natural conditions in everyday life, audio and tactile feedbacks are uncoupled. So it's not going to be a big problem to go further into the uncoupling and making both feedbacks independent. And so, well, that's pretty much it for the context. You can see the present study as a preliminary phase to Paul's PhD in order to gather some qualitative and start data. And we're going to extend this ability to change auditory and tactile feedback also to visual modality. So if you are here today, I guess you're all convinced that multimodality is really important, and you start, I think you know multimodal integration phenomena, so I'm not trying to be short here, just giving a few arguments from the musical acoustics perspective. Why is it useful to study the link between vibrotactile and audio feedbacks, and what we expect here in our study. So there's quite a bunch of there's quite a bunch of literature on the topic, and for example, it's been proven that with keyboard instruments, if you have a hard time pushing the keys, so if the keys are hard to press, then you'll have the feeling that the sound is much louder, for example. There have been many interesting studies on the violin, including those by Vollmann and others, proving that if you're increasing the vibrotactile feedback of a violin when playing it or when actively listening to it, then you're changing the judgments on auditory features. So making the violin vibrate more will make you judge the violin as more powerful or louder, for example. And it goes even further. If you have a violinist play with auditory masking, so the violinist only has tactile cues, The violinist will be able to judge sound-related aspects like loudness or sound richness, etc. And we conducted some interviews with guitar players, and they tell you the same. Like, so they often, I'm not going to read those citations, but they often merge the feelings of sound and vibration. So they're really intricate, and they both contribute to the judgment of sound. And a few arguments on the, well, maybe I should display everything here, on the combination of visual and audio feedbacks. So when we conducted many interviews with professional electric guitar players, and they're able to tell you things like guitars that have a neck with a black wood have a warmer sound. And we see many citations like this one, like showing that only seeing the instrument, so in this case guitar, provides you with expectations in sound. And if you go further, you have, for example, this guy saying, the instrument itself shall not claim something eccentric or so. So this is my translation of French. I guess it's not so weird. And it is important because you look at the instrument and you show it, meaning you show it to the people. And when you play, you are in some cultural world, so your instrument is not neutral. So that means that, and this one and other guys really mean that when you see the instrument, when you have a visual interaction with the instrument, that will kind of change the intention, what you want to play with this guitar in that case. That will change your actions and the gesture. So let's go for the objectives of this study. Again, so the warning is this is work in progress, so this is why I spend much time on context. And so what we want to explore here is the fact that when you see and touch the instrument, so when you're playing the instrument, all your visual and tactile cues, they make you remember of previous experiences and previous experiences of playing guitar, which will influence your expectations, such that that goes in 2 points. It will maybe change the way you are playing the guitar. So depending on what you get from the vision or tactile cues, then you will maybe choose to play another music style or with different techniques. And second, perception of the sound itself will be modified by visual and vibrotactile cues, as for example with the keyboard instruments or anything. Like if the instrument is vibrating much more, then you will maybe have the impression that it sounds louder. Well, so that's what we're going to do here. We're going to have guitar players play with the guitar, in which the audio, the vibrotactile, and visual feedbacks can be modified by the player, him or herself. That's I guess, the originality of our work. It's not imposed by the experimenter, it's controllable by the player. So very briefly on the methods. So I try to keep it in 15 or 20 minutes, but if I'm late, just tell me. So we provided 2 settings for modifying the audio feedback of the instrument, taking the output of the microphone of the instrument, real-time processing it, and then sending the sound, processed sound to the amplifier. And we have 2 settings for the player. One is the audio volume, so very simple to understand. And second is an audio effect, and we chose the tremolo effect here. So if you don't know it, it's just think about an amplitude modulation. So the amplitude or the volume is modulated like with, I think there was a sine wave. So with the effect control, you're able to change the speed and depth of the amplitude modulation. We modified the vibrotactile feedback by doing the same, taking the microphone output real-time processing it with a computer and sending it to an amplifier and then an exciter. That's a voice core technology. And the actuator is actually glued to the head of the guitar. Two settings, volume and vibrotactile effect, which is not very classical. And we chose something that we think it can be connected in some way to the audio tremolo. And what we chose is, so the setting controls the balance between a clean and a noisy signal. Noise signal being some kind of a train of impulsions with not easy to recognize frequency. And at last, we also modified the visual feedback by using this. I don't know if it's clear here. So imagine you have a depth camera in front of you for playing the guitar, and we have an algorithm called Reveal, which is capable of identifying the markers on the guitar, so identifying the position and orientation of the guitar. And it's coupled with a video projector that is projecting a texture, an image on the guitar. And the controls are the following. So the kind of visual volume, which is only the intensity of light, and a visual effect. So again, that's not really classical, even, especially if players are expected to modify it. But still, visual effect controls the size, density, and the shape of some grain onto the fingerboard of the guitar. Illustration. This is the smoothest so it's not smooth anymore. Texture. My internet.
Okay, so we have some connectivity issues.
Sorry. I guess you kind of hear me.
You can repeat, you had connectivity issues, so maybe now it's fixed.
Okay. I only have the beginning of your sentence. Lost me?
No, we did not lose you, but it's a very weak signal.
Running.
Okay, we have lost our last panelist. So unfortunately, one suggestion would be that he could record his presentation, and we will put it in the on our website so that you can follow it until the end. We can wait we can wait 2 more minutes. Maybe he's back. I can see his name on the. So you're back, Arthur? Maybe you can switch off your camera.
Sorry, it keeps interrupting. I don't know, back for good or not.
So maybe you can stop your
Try
video.
to find another spot.
Can you stop your video? Okay, so can you hear me? So Arthur, maybe we have lost you. So we have lost you. So can you hear me?
Okay, so I'm really sorry. Is it good now?
Yes, we can hear you. Can you hear me?
Yes, I can. It's
okay. So maybe okay.
Quality is not very good, but that's okay. So let's try to go back. So I guess you see my screen now.
Yes, that's the slide before.
Okay. So did you see it? Did you have the story till the visual feedback modification?
Yes.
Maybe you can go to the next slide, Arthur.
Okay. Try to go back to the presentation. So this is just the view from the perspective of the setup here. And this is just to recall the controls that we give player. So we have two sliders controlling the volume and the for vibrations, and two other sliders for the visuals. So, so the tests that we conducted were in phases. One phase was the free exploration and playing of the guitar and setup. Freely play and express their play with the guitar and with the interface, and freely express what they thought, what they felt. And the second, more calibrated one, say, where we use and visual effect, a minimum or maximum value, and we asked the players to set settings in order to reach some.
Arthur, I'm sorry, I apologize, but your voice is cut every seconds, so it's very hard to follow you. Arthur. So my suggestion is that you make a record of your presentation, and we will put it on the website. Really apologize.
Sorry, it looks like I was disconnected. Now I'm back. I don't understand. You also guess you don't see my screen.
Arthur, you're cut. Your voice is cut each seconds. Okay, so
yeah, okay.
So I think that the best option would be to record your presentation, and we will put it on the website.
Okay, I can do it.
Apologize.
Yeah, I'm really sorry for it. That's my bad.
No, but not sure. Right? But we have this. We can make it with the presentation. We can record it, and I think it will be okay. It's due to the fact that we are at distance. We make it virtually. No, don't be sad.
Okay, so I try to do a nice movie.
Okay, so
Thanks, Olivier.
so this was our last presentation. So maybe we can thank our panelists again and for their nice presentations. I would like also to thank you to have attended this workshop till the end. So thank you very much. Thank you very much to the organizers of this World Haptic conferences, and I really hope you enjoyed all the presentations in the very different ways to think about multimodal touch input devices. And if you have any comments, you can send an email to me, Frédéric Giraud, or to the other panelists, and their name and their email addresses are written on the website. So let me thank all of you again, and say you have a nice conference and have a nice weekend. So thank you and goodbye.